Maximum likelihood estimation. So suppose that you make some observations, y1, y2, all the way up to yn, and you strongly believe that these data values are coming from some particular distribution. Maybe it's normal, maybe it's Bernoulli or binomial or whatever. But so you believe in the form of the distribution. You just don't know the parameters. For example, for the normal, maybe you don't know what the mean is, and you don't know the standard deviation, and you want to estimate those. Or if you strongly believe these things are Bernoulli random variables, meaning that they take on values of 0 or 1 with a certain fixed probability p, and you just don't know p, then you want to use your data to estimate these distribution parameters. So we can do this with the method of maximum likelihood. If the data are coming from a discrete distribution, then the likelihood function L is just the conditional probability that you'd observe the data that you actually did observe given the parameter values. And it's treated as a function of the parameter values. So these thetas, if you don't like these, think of these thetas like for the case of a normal, then the thetas would be mu and sigma, because those are the two parameters for a normal. Or in the case of a Bernoulli, then the theta here would be a p. So the likelihood function is, you can think of it as a conditional probability function of it's the conditional probability of these variables taking on the data values that you actually observed given these parameter values. So for example, let's say you believe wholeheartedly that your data values are indeed coming from a Bernoulli p distribution. That means that for each one of these y's, say yi equals 1 with probability p and 0 with probability 1 minus p. Okay, then the likelihood function here is just the chance that y1 is that the random y1 takes the value of the first one that you saw, and the random y2 would take the value of the second one that you saw, and so forth, conditioned on the value of p. So where we're going with this is that we want to under the assumption that you're actually sampling from a Bernoulli distribution, we want to estimate the p here, the parameter here, that maximizes the chance that you would see what you actually saw. Okay, so we're maximizing this likelihood function. That's what we want to do. We want to maximize this likelihood function with respect to p. We want to find the value of p that maximizes this likelihood function. Okay. So oftentimes we assume that that our random samples are taken to be independent, and so in this case the likelihood function is just the product of the individual likelihood functions. Or again, these are just conditional probability functions. It's just the product of the probability that, say each one of these equals the whatever it is that we saw given p. In the case of this is in the case of in the Bernoulli case, okay, this just works out to be all this stuff, right? Because I'm going to have what's the chance that see all these little yi values are going to be 1s or 0s, okay? So what's the chance that big Y1 takes on the value of, say, 1? Well, it's p. Okay, and what's the chance that big Y1 takes on the value of 0? That's 1 minus p. So what's so you should be able to see that each one of these factors in this product will either be a p or a 1 minus p, right? Given the value, the true value of the parameter, what's the value that one of these random variables equals 1 or 0, say? If this is a 1, then I get a p here. If this is a 0, it's 1 minus p. So it should be p multiplied by itself, however many times we see ones here, and 1 minus p multiplied by however many times you see zeros there. So it's just p raised to the sum of the ones and zeros, which is the number of ones, and 1 minus p raised to the rest of it, right? Okay, so this is the likelihood function for the Bernoulli case. It might make sense to try to maximize this likelihood function over all values of p. We could differentiate twice and check for concavity, and of course, actually, we would see that this function is indeed concave downward. Some cases, like in the homework, you may have to remember to check boundary points. Okay, you might not be able to find the maximum that way. You might have to check the behavior at the boundaries. Turns out a lot of times it's easier to maximize the natural log of the likelihood function, because the log function, as you recall, is monotone increasing. So it turns out that maximizing some function f with respect to x will be the same as maximizing the log of f. The maximums of these will not be the same, but the x values that do the maximizing will be the same. Okay, if x maximizes the log of f, then x maximizes f. Okay, and it turns out that the logs of products result in sums, and it's often easier to differentiate sums than products. Okay, and so you'll see that, oftentimes we get products up here in the likelihood function. So if I take a log of a product, it's going to be the sum of the logs. What happens in the continuous case? Well, in the continuous case, you can't write the likelihood function as a product of probabilities, because the probability that a continuous random variable takes on any one particular value is going to be 0. So instead, what we do is we write the likelihood function to be the product of conditional density functions. Okay, these are our density functions. Remember that the density function for a random variable x times dx. This is essentially it's like the chance that our random variable x takes on a value between, say, x and x plus dx. Okay, it's yeah, like so. Okay, so so that's how we'll tackle this in the continuous case. So the maximum likelihood estimator, which we'll abbreviate with MLE, of a distribution parameter, is just taken to be the value of that parameter that maximizes the likelihood function L, or the log likelihood function. So here's an example. Suppose that these values are indeed from a Bernoulli P distribution. You want to estimate P. Of course, you could use the unbiased estimator. P hat equals just the average of those values, right? The sample mean. But let's try the maximum likelihood approach. If I take, let's begin by writing down my likelihood function, which is right, n given P. This is just the product of, because they're independent, it's just the product of the probability of each one of these equaling what it was that we actually saw, conditioned on the actual value of P. And now, and all this was on that other page, but this is just going to be P times however many of these y's are 1s, which is just the sum of the yks, right? Up to n. And then times 1 minus P raised to n minus the sum of those yk, k equals 1 to n. Okay? Now, I'm going to take the log of this likelihood function and then differentiate that guy. And so if I take the log of this likelihood function, can I just write it like this? Please let me write it like that. Okay. I'm just going to take the log of all that stuff. Remember, the log of the product is the sum of the logs. The log of the product is the sum of the logs. So I'm going to get that this is the sum of, let's see, k goes from 1 to n, of the log of p to the y sub k, plus log of 1 minus p to the n minus log of 1 minus p to the sum of the yk, k equals 1 to n. Okay. Of course, I could bring this sum down, and I could bring this n down, right? This will be, so all of this is, actually I get, what, log of p times the sum of the yk, k goes from 1 to n, is this first stuff here, plus n log of 1 minus p, minus the sum yk, k equals 1 to n, times the log of 1 minus p. Now, in fact, let's see, all of this stuff is, all of this is log p, sorry, log of 1 minus p times quantity n minus the sum of the y's. Okay? And now I'm going to differentiate all this stuff. So I'll take the derivative of all this stuff with respect to p. I just write it like this. I'm differentiating the log likelihood function with respect to p, because I want to find the value of p that maximizes the chance that we'd see actually what we saw. So this is, let's see, if I differentiate this first part here, this is a constant with respect to p, so it's just, this comes out, and the derivative of log of p is going to be 1 over p. Okay, and then let's see, all of this stuff is constant with respect to p, and the derivative of this stuff with respect to p is going to be negative 1 over p. So I get negative 1 over p times n, oops, sorry, negative 1 over 1 minus p times n minus the sum yk, k equals 1 to n, like so. And then now I'm going to set this equal to 0. Setting to 0 gives, at this point, when I set this equal to 0, then the value of p that solves that is going to be our maximum likelihood estimator. So I'm gonna write it like this: hat for estimate, MLE for the kind of estimate. Okay, just to indicate that this is our maximum likelihood estimator. Equals 1 over 1 minus p MLE times n minus sum of the yk. Okay. And yeah, so all this means then if I multiply through by this and that, I get 1 minus p hat MLE times the sum of the yk. Just going to abbreviate it like that, if that's okay. P hat MLE times n minus the sum of the yk. Okay, and yeah, if I do a little bit of algebra here, I get that this, I get the sum of the yk here is p hat MLE times the sum of the yk plus n times p hat MLE minus p hat MLE times the sum of the yk. And let's see, these will cancel, and I get that the sum of the yk is my estimate times n, or p hat MLE, in fact, is, hey, look, it's just the average of the y's. Okay, so it turns out that the maximum likelihood estimator in this case is in fact exactly the same as the unbiased estimator, which we've used always to estimate proportions, right? It's just the average of the ones and zeros. It's our sample proportion. Okay, doesn't always work out that the maximum likelihood estimator is the unbiased one, and we'll see examples